Welcome. My name is Sean Havens, and this presentation is part of my Google Data Analytics capstone portfolio. My background combines military leadership, business education, and a growing technical foundation in data analytics. I completed my MBA, and through this capstone project, I am applying data analysis tools to a real-world business problem: how manufacturing organizations can use operational data to reduce unplanned equipment failures. This project is titled Predictive Maintenance Analytics: Reducing Unplanned Equipment Failures in Manufacturing Operations. The purpose of this case study is to examine machine operating data and determine whether failure risk patterns can help leadership make better maintenance decisions. In manufacturing, unplanned machine failure can create more than a repair problem. It can disrupt production schedules, increase labor costs, reduce throughput, and affect customer delivery timelines. For this project, I used the AI4i 2020 Predictive Maintenance Dataset and analyzed the data in Google BigQuery. The analysis focuses on machine operating conditions, product type, tool wear, machine failure indicators, and failure modes. This presentation is structured as a management review. That means the goal is not only to show technical analysis. The goal is to translate the analysis into a practical business decision that leadership could evaluate and test. The central question guiding this presentation is: where is machine failure risk concentrated, and what maintenance action should leadership test first? By the end of this presentation, the data will support a focused recommendation. Test a preventive maintenance trigger before machines reach the high-risk tool wear threshold, with initial priority placed on product type L machines. Because this project uses a synthetic dataset and does not include cost, downtime duration, machine criticality, or maintenance history, the recommendation is not immediate full-scale implementation. The responsible next step is a controlled pilot program to validate the finding in a real operating environment. Manufacturing organizations depend on reliable equipment to keep production moving. When a machine fails unexpectedly, the impact is usually larger than the repair itself. An unplanned equipment failure can interrupt production flow, delay work orders, increase maintenance labor, create overtime requirements, reduce throughput, and affect customer delivery timelines. In some cases, a single failure can disrupt an entire production schedule if the failed machine is part of a critical process. The business problem in this project is that reactive maintenance gives leadership limited time to respond. If maintenance teams only act after a machine fails, the organization is already absorbing the cost of downtime, repair work, and schedule disruption. A more effective approach is to identify warning signs before failure occurs. This is the purpose of predictive maintenance analytics. Instead of waiting for a breakdown, the organization uses machine operating data to detect patterns that may indicate rising failure risk. For this case study, the central business challenge is to determine whether the available data can help leadership identify where machine failure risk is concentrated and whether a practical maintenance trigger can be tested. This matters because the goal is not simply to analyze machine failures after they happen. The goal is to support better operational decisions before those failures create disruption. In this project, the analysis focuses on machine conditions such as tool wear, torque, temperature, product type, and failure modes. These variables are used to evaluate whether certain machines or product groups show higher risk and whether maintenance resources can be prioritized more effectively. The business problem can be summarized this way: leadership needs a data-driven way to move from reactive maintenance to targeted preventive maintenance without creating unnecessary maintenance activity or production delays. The purpose of the analysis is to determine whether machine operating data can identify useful failure risk patterns before failures occur. The goal is not only to count failures after the fact. The goal is to help leadership understand where risk is concentrated and what maintenance action should be tested first. The central question guiding this project is: where is machine failure risk concentrated, and what maintenance action should leadership test first? To answer that question, the analysis was organized around 4 smaller, decision-focused questions. The first question is overall risk. What is the baseline machine failure rate? This establishes the starting point for the analysis. Before we can determine whether a product type, operating condition, or toolware level is high risk, we first need to know the normal failure rate across the full dataset. The second question is segment risk. Which product types experience the highest failure risk? This helps determine whether failures are evenly distributed across product categories or concentrated in a specific segment. If one product type has both higher failure risk and larger production volume, it may become the logical starting point for a maintenance pilot. The third question is failure drivers. Which failure modes appear most frequently? This helps leadership understand what types of operating stress may be connected to machine failure. If failures are mostly random, preventive action becomes harder. But if failures are connected to heat, strain, power, or wear, then maintenance teams may be able to monitor those conditions before breakdown occurs. The fourth question is maintenance threshold. Does toolware identify a practical preventive maintenance trigger? This is the most action-oriented question in the project. If failure risk increases sharply after a certain level of toolware, leadership may be able to test an early inspection point before machines enter the highest risk zone. Together, these four questions move the project from general analysis to practical decision support. The analysis begins with the baseline failure rate, then identifies high-risk segments, reviews likely failure drivers, and finally tests whether toolware can guide preventive maintenance action. The key takeaway from this slide is that the project is designed to answer a business decision, not just produce technical results. The goal is to identify where failure risk is concentrated and determine what maintenance action leadership should test first. This slide explains the workflow used to move from the dataset to a management-ready recommendation. The process began with a cleaned CSV dataset. This file contained 10,000 machine observations from the AI 4i 2020 Predictive Maintenance Dataset. Each observation included information about product type, operating conditions, toolware, machine failure status, and failure modes. After the dataset was cleaned and prepared, it was uploaded into Google BigQuery. BigQuery served as the primary analysis environment because it allowed the data to be queried using SQL and made the analysis reproducible. This was important because the project needed to show not only the final results, but also the logic used to calculate those results. The next step was creating and saving SQL queries. 7 named queries were developed for this analysis. These queries calculated the overall failure rate, compared failure rates by product type, identified failure mode counts, compared failed and non-failed machine profiles, analyzed toolware bands, examined high-wear product risk, and estimated potentially avoidable failures. Saving the queries was an important part of the workflow. In a professional setting, analysis should be traceable. A supervisor, reviewer, or coworker should be able to understand how a result was produced and repeat the analysis if needed. After the analysis was completed, the findings were organized into a formal business report. The report explains the business problem, the dataset, the methodology, the findings, the limitations, and the management considerations before making recommendations. The final step is this PowerPoint presentation. The purpose of the presentation is to translate the report into an executive decision support format. Instead of showing every detail from the analysis, the presentation focuses on the most important findings, the business meaning behind those findings, and the recommended next step. This workflow reflects a practical data analyst process. Prepare the data, analyze it with a reliable tool, document the logic, report the findings, and communicate the recommendation clearly to decision makers. The key takeaway from this slide is that the project is designed to answer a business decision, not just produce technical results. The goal is to identify where failure risk is concentrated and determine what maintenance action leadership should test first. The purpose of this slide is to show the core calculations behind the project findings. These calculations establish the baseline failure rate, identify where risk becomes concentrated, and support the estimated avoidable failure opportunity. The first calculation is the overall failure rate. This was calculated by dividing total machine failures by total records. In the dataset, there were 339 machine failures across 10,000 total machine observations. That produces an overall failure rate of 3.39%. At a surface level, 3.39% may not appear extremely high. However, in a manufacturing environment, even a relatively small failure rate can create real operational consequences. A failure can interrupt production flow, increase repair labor, delay schedules, and create delivery risk. For that reason, the overall failure rate serves as the baseline, but it does not tell the full story. The second calculation is the product type failure rate. This was calculated by dividing failures within each product type by total records for that product type. Product type L had 235 failures across 6,000 records, producing a failure rate of 3.92%. This was the highest observed failure rate among the product categories. This finding matters because product type L is not only the largest product group in the dataset, it also has the highest failure rate. That combination makes product type L an important segment for management attention. The third calculation is the high wear failure rate. This focuses on machines with tool wear of 200 minutes or greater. The high wear group had 123 failures across 801 records. Dividing 123 by 801 produces a failure rate of 15.36%. This is one of the most important findings in the project. The high wear failure rate is much higher than the overall failure rate. It indicates that once tool wear reaches 200 minutes or more, machine failure risk rises sharply. The fourth calculation is the below 200 baseline failure rate. This was calculated by looking at machines with tool wear below 200 minutes. In that group, there were 216 failures across 9,199 records. That produces a baseline failure rate of 2.35%. This comparison is critical. Machines below 200 minutes failed at 2.35%, while machines at 200 minutes or higher failed at 15.36%. This difference suggests that the 200-minute tool wear point is a meaningful risk threshold. The fifth calculation estimates how many failures would be expected in the high wear group if that group performed at the below 200 baseline rate. The high wear group had 801 records. Multiplying 801 by the below 200 failure rate of 2.35% gives an expected failure count of approximately 19. This does not mean that exactly 19 failures would occur in a real plant. It is a scenario estimate. It asks a practical management question. If the high wear group could be brought down to the lower risk baseline, how many failures might be expected? The final calculation estimates the avoidable failure opportunity. The high wear group currently had 123 failures. The baseline estimate suggested approximately 19 expected failures. Subtracting 19 from 123 gives an estimated 104 potentially avoidable failures. This number is important because it translates the analysis into a business opportunity. It suggests that a targeted maintenance strategy focused on machines approaching the 200-minute tool wear threshold could potentially reduce a meaningful share of failures. However, this estimate must be interpreted carefully. It is not a guaranteed savings figure. The dataset does not include cost per failure, downtime duration, equipment criticality, maintenance capacity, or production scheduling constraints. Therefore, the 104 avoidable failures should be treated as a decision support estimate, not a confirmed operational result. The key takeaway from this slide is that the overall failure rate was 3.39%, but failure risk was not evenly distributed. The 200-plus tool wear group failed at 15.36%, compared with only 2.35% below 200 minutes. That gap supports the recommendation to test a preventive maintenance trigger before machines enter the highest risk wear range. The dataset contained 10,000 machine observations. Out of those observations, 339 machine failures were recorded. Dividing 339 failures by 10,000 total records produces an overall failure rate of 3.39%. At first glance, 3.39% may appear relatively low. However, in a manufacturing environment, even a low failure rate can create significant operational cost. Machine failures can lead to downtime, repair labor, schedule disruption, scrap, reduced throughput, and delayed customer delivery. This finding is important because it establishes the baseline for the rest of the analysis. The overall failure rate gives leadership a reference point for determining whether certain product types, operating conditions, or toolware levels show elevated risk. In other words, the 3.39% failure rate is not the final conclusion. It is the comparison point. Once the baseline is established, the analysis can determine where the risk is concentrated and whether certain machine groups fail at a much higher rate. The key takeaway from this slide is that the overall failure rate provides the starting point for the analysis. The baseline appears modest, but it allows us to identify the segments where machine failure risk rises above normal operating conditions. This slide presents the second key finding from the report. Product type L had the highest overall failure risk. The analysis compared failure rates across the three product categories: product type L, product type M, and product type H. The purpose was to determine whether failure risk was evenly distributed across the dataset or concentrated in a specific product group. The results show that product type L had the highest observed failure rate. Product type L recorded 235 failures across 6,000 records, producing a failure rate of 3.92%. By comparison, product type M recorded 83 failures across 2,997 records, producing a failure rate of 2.77%. Product type H recorded 21 failures across 1,003 records, producing the lowest failure rate at 2.09%. The chart on the right shows this difference clearly. Product type L had the highest failure rate, followed by product type M and then product type H. This finding matters because product type L stands out in two ways. First, it had the highest observed failure rate. Second, it also represented the largest production segment in the dataset. That means product type L combines higher risk with greater operational exposure. From a management perspective, that combination makes product type L the strongest candidate for the first maintenance pilot. If leadership wants to test a preventive maintenance strategy before expanding it across the full operation, product type L provides the clearest initial focus. Product types M and H should not be ignored. They should remain under review as secondary monitoring priorities. However, based on the combination of failure rate and production volume, product type L should be prioritized first. The key takeaway from this slide is that product type L is the strongest candidate for the first maintenance pilot because it has both the highest observed failure rate and the largest production segment. This slide presents the third key finding from the report. Most failure modes appeared connected to operating stress rather than random breakdown. The analysis reviewed the recorded failure categories in the dataset to determine which types of failures occurred most often. The leading failure mode was heat dissipation failure, with 115 recorded instances. This suggests that thermal stress may be a major contributor to machine failure risk. The second most common category was overstrain failure, with 98 recorded instances. Overstrain failure points toward mechanical stress, excessive load, or equipment operating under pressure beyond normal tolerance. The third major category was power failure, with 95 recorded instances. This may indicate stress related to power demand, motor load, or operating conditions that place additional strain on the equipment. By comparison, toolware failure appeared 46 times, and random failure appeared only 19 times. The low number of random failures is important because it suggests that many machine failures were not purely unpredictable events. From a management perspective, this matters because measurable failure patterns are more actionable than random breakdowns. If failures are connected to heat, strain, power load, and wear, then maintenance teams can monitor these conditions and respond before a failure occurs. This finding supports the broader recommendation for condition-based maintenance. Instead of relying only on reactive repairs after breakdown, Leadership can use operating indicators to identify where failure risk may be increasing. The key takeaway from this slide is that the largest failure categories were tied to measurable operating stress. That makes the case stronger for a preventive maintenance pilot using early warning indicators. This slide presents the fourth key finding from the report. Failed machines showed a different operating profile than machines that did not fail. The purpose of this comparison was to determine whether machine failure was associated with measurable operating differences. If failed and non-failed machines looked mostly the same, it would be harder to justify a condition-based maintenance approach. However, the analysis showed clear differences across several operating variables. The largest difference was in tool wear. Machines that did not fail had an average tool wear value of 106.69 minutes, while machines that failed had an average tool wear value of 143.78 minutes. That is a difference of 37.09 minutes. This suggests that higher tool wear was strongly associated with failure risk. The second important difference was torque. Non-failed machines had an average torque of 39.63 Newton meters, while failed machines had an average torque of 50.17 Newton meters. That is an increase of 10.54 Newton meters among failed machines. From an operational standpoint, this may indicate that machines under greater mechanical load or strain were more likely to fail. The temperature differences were smaller, but still moved in the same direction. Failed machines had a slightly higher average air temperature and a slightly higher average process temperature than non-failed machines. This supports the broader pattern that failure risk was associated with operating stress. The radar chart on the right visualizes these differences. The strongest positive difference appears in tool wear, followed by torque. The smaller temperature differences are also shown, while average RPM moved in the opposite direction. RPM was lower among failed machines. This is important because it suggests that failure risk was not simply caused by faster operation. Instead, the risk appears to be connected to a combination of wear, load, and operating stress. From a management perspective, this finding supports the case for condition-based maintenance. Maintenance decisions should not rely only on fixed schedules. They should also consider measurable operating conditions, especially tool wear, torque, and temperature. The key takeaway from this slide is that failed machines had measurable operating differences. Those differences can help leadership identify warning signs before failure occurs. This slide presents the strongest finding in the analysis. Failure risk increased sharply after machines reached 200 minutes of tool wear. The purpose of this analysis was to determine whether tool wear could serve as a practical warning signal for preventive maintenance. To test that, tool wear was grouped into bands, and the failure rate was calculated for each group. The first 4 tool wear bands remained relatively stable. Machines in the 0 to 49 minute group had a failure rate of 2.21%. Machines in the 50 to 99 minute group had a failure rate of 2.25%. Machines in the 100 to 149 minute group had a failure rate of 2.27%. Machines in the 150 to 199 minute group increased slightly to 2.66%. Taken together, the data shows that failure risk remained low and fairly consistent below 200 minutes of tool wear. The major change occurred at 200 minutes or greater. In the 200 plus tool wear group, the failure rate increased sharply to 15.36%. This is the clearest threshold identified in the project. The chart on the right shows this pattern visually. The lower wear bands are clustered near the bottom of the failure rate scale, while the 200 plus group extends much farther across the chart. That separation makes the 200-minute threshold stand out as a practical maintenance signal. From a business perspective, this finding matters because it gives leadership a specific point for action. Machines approaching 200 minutes of tool wear should not be treated the same as machines operating at lower wear levels. They should be reviewed, prioritized, or scheduled for inspection before entering the highest risk range. The 200 plus group failed at about 6.5 times the below 200 baseline. That does not mean every machine above 200 minutes will fail. Most machines in that group still did not fail. However, the increase in risk is large enough to justify a controlled maintenance pilot. This is why the recommendation is not to wait until machines cross the 200-minute point. The practical management action is to create an alert before that threshold, such as 180 minutes, so maintenance and production leaders have time to plan inspection or service without creating unnecessary disruption. The key takeaway from this slide is that 200 minutes of tool wear is the clearest maintenance trigger point identified in the analysis. It provides a practical basis for testing a preventive maintenance review before failures become more likely. The previous finding showed that failure risk increased sharply once tool wear reached 200 minutes or greater. This slide takes the analysis one step further by asking which product type had the greatest risk inside that high wear group. The results show that product type L had the highest high wear failure rate. Among machines with 200 minutes or more of tool wear, product type L had 503 high wear records and 92 failures. That produced a high wear failure rate of 18.29%. Product type H also showed elevated risk, with 75 high wear records, 8 failures, and a failure rate of 10.67%. Product type M had 223 high wear records, 23 failures, and a failure rate of 10.31%. All three product types showed increased risk above the 200-minute threshold. However, product type L stands out because it had both the highest failure rate and the largest number of high wear records. That means product type L combines higher risk with greater exposure. This distinction is important for the pilot recommendation. If leadership wants to test a preventive maintenance trigger before expanding it across the full operation, the first pilot should begin where the data shows the strongest concentration of risk. Based on this analysis, product type L is the strongest candidate for the first maintenance pilot. Product types H and M should remain under review, but they are lower initial priorities because their high wear failure rates and exposure levels were lower than product type L. The key takeaway from this slide is that product type L should be the first high wear maintenance pilot segment because it combines the highest failure rate above 200 minutes with the largest high wear population. The purpose of this calculation is to estimate the size of the prevention opportunity in the high wear group. Earlier in the analysis, the data showed that machines with tool wear of 200 minutes or greater had a much higher failure rate than machines below 200 minutes. The question here is, what might happen if the high wear group could be brought closer to the lower risk baseline? The high wear group had 123 recorded failures. These are the actual failures observed among machines with 200 minutes or more of tool wear. Next, the analysis estimated how many failures would be expected if that same high wear group performed at the below 200 baseline failure rate. Based on that calculation, the expected number of failures would be approximately 19. The difference between those two numbers is the estimated opportunity. Subtracting 19 expected failures from 123 current high wear failures produces 104 potentially avoidable failures. This estimate is important because it translates the tool wear threshold into a business decision. It suggests that the high wear group is not just statistically different, it may represent a meaningful operational opportunity. The slide also shows the size of that opportunity compared with all failures in the dataset. The dataset contained 339 total machine failures. The 104 potentially avoidable failures represent approximately 30.7% of all recorded failures. That is a substantial share. If a maintenance pilot could reduce even part of that failure burden, the operational impact could be meaningful. However, this number must be interpreted carefully. The 104 failures are not guaranteed savings. This is a scenario estimate based on comparing the high wear group to the below 200 baseline failure rate. The dataset does not include cost per failure, downtime duration, repair labor, equipment criticality, or maintenance capacity. For that reason, this finding should be used as decision support, not as a final claim of guaranteed prevention. The management meaning is that the opportunity is large enough to justify a controlled pilot. The organization should test whether earlier inspection or service before the 200-minute tool wear threshold can reduce failures without creating excessive maintenance workload or unnecessary production disruption. The key takeaway from this slide is that the data identifies a measurable prevention opportunity. A focused maintenance pilot may be able to reduce a meaningful share of failures, but the estimate must be validated in real operations. Now we move from the findings into management considerations. The analysis identified a clear risk pattern. Machines with tool wear of 200 minutes or greater had a much higher failure rate, and product type L was the strongest pilot candidate. However, before leadership acts on the findings, several important considerations must be addressed. First, the dataset is synthetic. It was designed to reflect realistic industrial predictive maintenance conditions, but it was not collected directly from a live manufacturing facility. That means the findings are useful for analysis and decision support, but they should be validated with real plant data before becoming permanent operating policy. Second, the dataset does not include several business-critical fields. It does not include cost per failure, downtime duration, replacement part cost, labor cost, maintenance history, or equipment criticality. Because of that, the analysis can estimate potentially avoidable failures, but it cannot calculate the exact financial return on investment. Third, there is a risk of false positives and over-maintenance. Although machines above 200 minutes of tool wear had a much higher failure rate, most machines above 200 minutes still did not fail. If leadership created a strict automatic maintenance rule, the company could create unnecessary inspections, increase labor workload, or disrupt production unnecessarily. Fourth, the proposed 180-minute alert point should be treated carefully. The analysis supports the 200-minute threshold as a strong risk signal. However, 180 minutes is a management buffer designed to give maintenance teams time to act before machines reach the high-risk zone. It should be tested, not assumed. The management conclusion is that the findings support action, but not immediate full-scale implementation. The responsible next step is a controlled pilot focused on product type L machines approaching the 200-minute tool wear threshold. The key takeaway from this slide is that the analysis is strong enough to justify testing, but not strong enough to become permanent policy without validation. This slide presents the main business recommendations from the analysis. The first recommendation is to pilot an inspection trigger before machines reach 200 minutes of tool wear. The analysis showed that failure risk increased sharply once machines reached the 200-minute threshold. Because of that, leadership should not wait until machines are already in the highest risk range. A practical approach is to create an early alert before that point, such as 180 minutes. So maintenance teams have time to inspect, plan, and schedule service before risk increases sharply. The second recommendation is to prioritize product type L during the first pilot. Product type L had the highest overall failure rate and the highest failure rate within the high wear group. It also had the largest number of high wear records. This makes product type L the strongest starting point for a controlled maintenance pilot. The third recommendation is to monitor tool wear, torque, and temperature together. Tool wear was the clearest threshold, but it should not be the only condition reviewed. Failed machines also showed higher average torque and slightly higher operating temperatures. A machine approaching the tool wear threshold, while also showing elevated torque or temperature, should receive higher inspection priority. The fourth recommendation is to build a maintenance risk dashboard. This dashboard should track machines approaching the alert point, machines already above 200 minutes, failure rates by product type, failure modes, operating profile indicators, and estimated avoided failures over time. The management purpose of these recommendations is not to immediately redesign the entire maintenance system. The purpose is to test a focused, evidence-based approach in the highest risk segment and measure whether it reduces failures without creating excessive maintenance burden. The key takeaway from this slide is that the analysis supports targeted testing. The recommended path is a controlled preventive maintenance pilot, not immediate company-wide rollout. This slide turns the analysis into an operational action plan. The recommendation is to launch a controlled 60-day pilot focused on product type L machines. Product type L is the recommended pilot group because the analysis showed that it had the highest overall failure rate and the highest high wear failure rate after the 200-minute tool wear threshold. The purpose of the pilot is to validate whether the 200-minute threshold can be used as a practical preventive maintenance signal before full implementation. The analysis showed that failure risk increased sharply once tool wear reached 200 minutes or greater. However, because the data set is synthetic and does not include cost, downtime, maintenance history, or equipment criticality, the threshold should be tested before becoming permanent policy. The pilot should begin by flagging product type L machines when they reach 180 minutes of tool wear. The 180-minute alert point gives the maintenance team time to inspect the machine and plan service before it reaches the higher risk 200-minute threshold. When feasible, machines should be inspected and serviced before reaching 200 minutes. This does not mean every machine should automatically be removed from production. The alert should support maintenance planning while still considering production schedules, maintenance capacity, and operational priorities. The pilot should also track whether the approach creates value without creating unnecessary burden. The key performance indicators on the right side of the slide are designed for that purpose. The first KPI is the number of machines flagged. This measures the intervention volume and shows how many machines would be affected by the alert rule. The second KPI is the failure rate after intervention. This is the main improvement measure. It helps determine whether the pilot actually reduces failures compared with the baseline. The third KPI is maintenance labor hours. This measures the workload impact on the maintenance team. The fourth KPI is downtime hours. This helps determine whether the pilot reduces disruption or unintentionally creates new operational delays. The fifth KPI is the false positive rate. This is important because most machines above 200 minutes did not fail. Leadership needs to know whether the alert creates too many unnecessary inspections or early service actions. At the end of the 60-day pilot, leadership should compare pilot results against the baseline failure rates identified in the analysis. If failures decline without excessive maintenance burden, the company can consider expanding the approach. If the results are mixed, leadership can revise the threshold or add other indicators such as torque and temperature. The key takeaway from this slide is that the pilot provides a controlled way to test the maintenance threshold before full implementation. It moves the project from analysis to action while protecting the organization from overmaintenance and unnecessary production disruption. The purpose of this slide is not to weaken the analysis. The purpose is to define what the analysis can and cannot prove. In a professional setting, strong recommendations should include both findings and limitations, especially when the recommendation could affect maintenance schedules, labor workload, production flow, and operating cost. The first limitation is that the dataset is synthetic. The AI4i 2020 Predictive Maintenance Dataset was designed to represent realistic industrial predictive maintenance conditions, but it was not collected directly from a live manufacturing plant. Because of that, the findings should be treated as useful decision support, not as automatic proof that the same threshold would perform identically in a real facility. The second limitation is that the dataset does not include direct cost or downtime duration. The analysis can show that certain machine groups failed more often, and it can estimate potentially avoidable failures. However, it cannot calculate the exact dollar impact of those failures. To calculate return on investment, leadership would need cost per failure, repair labor cost, replacement part cost, downtime cost, lost production value, and any customer delivery penalties. The third limitation is that the dataset does not include an equipment criticality ranking. In a real plant, not every machine has the same operational importance. A failure on a bottleneck machine or critical production line may be much more damaging than a failure on lower priority equipment. Without criticality data, the analysis treats all failures equally. The fourth limitation is that the dataset does not include maintenance history or machine age. That means the analysis cannot determine whether a failure occurred because maintenance was missed, delayed, ineffective, or because the machine was already near the end of its life cycle. The fifth limitation is that correlation does not prove causation. The analysis shows that higher tool wear, higher torque, and slightly higher temperatures were associated with failure. It does not prove that any one factor alone directly caused the failures. The sixth limitation is that this report does not build a predictive machine learning model. The analysis is descriptive and diagnostic. It identifies patterns, thresholds, and risk segments, but it does not predict the failure probability of each individual machine. The key takeaway from this slide is that the analysis identifies important risk patterns, but real-world validation is required before permanent implementation. This is why the recommendation is a controlled pilot, not immediate full-scale policy adoption. The purpose of this recommendation is to strengthen the business case. The current analysis identified important risk patterns, especially around tool wear, product type L, and the 200-minute threshold. However, to move from a pilot recommendation to a stronger long-term maintenance strategy, leadership would need additional operational and financial data. The first recommended data field is downtime hours per failure. The current dataset identifies whether a machine failed, but it does not show how long the failure disrupted production. In a real manufacturing environment, one failure may cause only a short delay, while another may stop a critical process for hours. The second recommended data field is cost per failure and repair labor. This would allow leadership to estimate the financial value of avoided failures. Without cost data, the analysis can estimate the number of potentially avoidable failures, but it cannot calculate a precise return on investment. The third recommended data field is maintenance history and service dates. This would show whether prior maintenance reduced risk, whether failures occurred after missed service intervals, and whether certain machines require more frequent inspection. The fourth recommended field is equipment criticality ranking. In practice, not every machine carries the same operational importance. Machines tied to bottleneck processes or critical production lines should receive higher maintenance priority than lower impact equipment. The fifth recommended field is machine age and life cycle stage. This would help separate failures caused by operating stress from failures related to aging equipment, long-term wear, or end-of-life asset conditions. The final recommended field is shift, operator, and production schedule data. Manufacturing performance is not only mechanical. It can also be affected by scheduling pressure, workload, shift patterns, and human system factors. The slide also identifies future questions. One important question is whether a 180-minute alert performs better than waiting until 200 minutes. Another is whether combining torque with tool wear improves risk detection. A third question is the dollar value of avoided failures. Finally, leadership should consider whether a live dashboard or predictive model could improve failure risk monitoring. The key takeaway from this slide is that additional data would help convert the pilot into a stronger cost-benefit and reliability strategy. The current analysis is strong enough to justify testing, but future data collection would make the decision more precise, measurable, and financially defensible. This final slide brings the analysis back to the management decision. The purpose of this project was to determine whether machine operating data could help leadership move from reactive maintenance to more targeted preventive decision-making. The analysis showed that the answer is yes, but with discipline, validation, and a controlled next step. Across 10,000 machine observations, the overall failure rate was 3.39%. That baseline gave us the starting point, but the deeper finding was that failure risk was not evenly distributed. The strongest signal appeared at the 200-minute tool wear threshold. Machines below 200 minutes had relatively stable failure rates. But once tool wear reached 200 minutes or greater, the failure rate increased sharply to 15.36%. The analysis also showed that product type L should be the first pilot segment. Product type L had the highest overall failure rate, the highest high wear failure rate, and the largest high wear exposure. In practical terms, that means product type L gives leadership the clearest place to test whether earlier maintenance action can reduce failures. The scenario analysis estimated that 104 failures may be potentially avoidable if the high-wear group could be reduced closer to the below 200 baseline failure rate. That represents approximately 30.7% of all recorded failures in the dataset. That number is important, but it should not be treated as a promise. It should be treated as an opportunity large enough to test, measure, and validate. That is why the decision request is not to launch a company-wide policy immediately. The responsible decision is to approve a controlled 60-day pilot focused on product type L machines. During the pilot, machines should be flagged at 180 minutes of tool wear. That alert gives maintenance leaders time to inspect, plan, and act before the machine reaches the 200-minute high-risk threshold. The pilot should track whether failures decline without creating excessive maintenance burden. It should also measure labor hours, downtime, false positives, and whether the alert point should be expanded, revised, or stopped. This is the value of data analytics in a business environment. The goal is not simply to produce charts or calculations. The goal is to help leaders make better decisions with less uncertainty. This project shows how operational data can identify risk, focus resources, and support a practical action plan. It also shows the importance of using data responsibly. The findings are strong enough to support action, but the limitations are real enough to require validation. The final takeaway is straightforward. The data supports action, but the responsible next step is controlled validation. By approving a 60-day product type L pilot, leadership can move from analysis to action, from reactive response to preventive planning, and from uncertainty to measurable operational learning. That is the decision request. Approve the pilot, measure the results, and use the evidence to decide whether to expand, revise, or stop the approach.